Good morning. So in this series of lectures on signals and systems, today I am going to discuss about the spectral densities, that is frequency domain representation of the LTI system response. So this is because the response is dependent on the input also. So the spectral densities of the input and output and the spectral properties of the LTI system I am going to discuss today. And here basically the theoretical part of this one I have discussed in my previous lecture. So this lecture is totally dedicated to simulations to understand the theory we have studied already. And in this simulations I use MATLAB package, and I have my own customized functions for all. And first I apply the energy input signal, and afterwards I will apply the periodic signal. So for both signals I will compute the spectral densities, and I will discuss why the shape is there, regarding this frequency distributions, and I will justify the spectral properties with respect to the shape of the input signal. So here this is the system which we have considered, and input x of t, output y of t, and LTI linear time invariant system has impulse response h of t. Then the frequency representation. What is the Fourier transform? Basically, the Fourier transform or Fourier spectrum of input signal is capital X, output signal is of y, output signal is y, and this is the frequency response of the system h omega. Now, in the frequency domain, as I discussed in my previous class, the output spectrum is equal to the product of the frequency response of the system and the input spectrum. And these are all relations, just for completeness I had put it. And so some energy density relations I will see, because first I am considering the energy signals, finite duration signals. So here the autocorrelation function of input. So in this one I think instead of double x in these equations I used only x, okay, because already I had these equations. So this is the autocorrelation of the input signal and energy spectral density, or sometimes we call it as energy density spectrum, sometimes we call, and both are same. So energy spectral density and autocorrelation of the input signal both form Fourier transform pair. So because this is a second order quantity and this is also a second order quantity. Okay. Similarly, the output, let me take the pointer. So similarly, the output autocorrelation function, and that means autocorrelation function of the output of the LTI system and energy spectral density of the output signal, they form the Fourier transform pair. And how these two are related, input power spectral density and output power spectral density, they are related, or they are weighed by this quantity. It is a function of frequency again, as expected, and this is the square of the magnitude of the frequency response. Okay, that is how these two are related. Now, similar things, if I take for power signals, these are the equations for power signals. So same equations basically, except for psi here, I am using capital S. Capital S represents the power spectral density. Psi x represents the energy spectral density. Otherwise, all these equations are similar to these equations. Okay. So now, let us take some more relations, but I consider the PSD relations here because it doesn't matter whether I take ESD or PSD. So here, this is, double X I am using. So this is, these two I already discussed. These two form the Fourier transform pair, and these two form the Fourier transform pair. And here is the new equation here. This is the cross correlation of RYX. So here, cross correlation of RYX and SYX. This is the cross power spectral density. This is called cross power spectral density. I will explain this, some theory about this. And these two form the Fourier transform pair. So here, basically when I take RX, RY, you take RY, I have YY double here, Y of omega square I have. Okay. So omega, Y of omega multiplied by Y of omega. One of these Y's will be replaced with X here. Okay. So Y of omega multiplied by X of omega. I am talking about the magnitudes here. Okay. So then this is equal to the cross power spectral density of the input signal and output signal. Okay. Of course, order is also important. And similarly, RXY and SXY, they form the Fourier transform pair. Okay. So let us see what is the importance of this cross correlation function is. Cross power spectral density. Basically, I have one spectrum. Let us say some spectrum is there, something like this. So this is some X of omega magnitude. Let us take another spectrum, something like this. In general, YX I am taking, they need not be related through any LTI system. They are independent things. I am considering like that. So now, this, what is the, let us say this is the omega, or you take F. So, 2 pi, let us say some 2 pi (2pi) 500 means at 500 Hz, this is the component at 500 Hz. Similarly, at this point, let us say it is 500 Hz. So I have, so because it is omega axis, I am adding 2 pi further down. Okay. So this is this frequency component and this frequency components, how they are correlated. That means basically it is also like a autocorrelation or cross correlation is also like a cross correlation, but correlation between two frequency components considered at a time. Okay, so that is what, because we are integrating again, because we have seen the expressions in the previous class. So this and this, I am correlating basically. Okay, that is what is the explanation. So how these frequencies are correlated? If the frequencies, one frequency in X of omega, is it correlated with the frequency in Y? That means, is there any trend? That means these two frequencies are related. That kind of relations within the spectrum, you will get. Okay. So, it is also similar to autocorrelation or cross correlation function, but this is the description of frequency components in the frequency domain. Okay. So this has, in fact, there, we have correlation coefficient, correct? So we have the correlation coefficient, normalized correlations we have, correlation coefficient. In the same way, here we have one quantity called coherence. Coherence. That means coherence between between the amplitudes of same frequencies in both spectra. Okay. So that is what is coherence. It is equivalent to the correlation coefficient there. So, and you have the bicoherence like that. Coherence, it finds several applications in ECG classification, signal classification you will find, and you will find several applications and everywhere, wherever you are using the auto cross correlation function for signal detection, signal estimation, okay, signal identification sometimes, very rarely. So that is there this coherence finds applications. Okay. So here, so that is what is importance of this cross power spectral densities, CPSDs. These are nothing but cross. So these are nothing but cross power spectral densities. Okay, so that is what is some new term in terms of spectra. So now let us consider this tiny equation, relation between output autocorrelation function and input autocorrelation function through this convolution. Okay, so that is equal to autocorrelation function of the impulse response basically, and this there is a convolve. Okay, the output autocorrelation is equal to the convolution of input autocorrelation function and the autocorrelation function of the impulse response. So these are related with the operator, convolution operator. So naturally, so when you convert into spectral domain, I get output power spectral density equal to input power spectral density multiplied by, convolution becomes multiplication, multiplied by the, what is this you call? So you call it a frequency response, square of the frequency response basically. This is square of the frequency, so square of the frequency, square of the frequency response basically. So it is like a, you should say square of the response, square of the frequency response of the, square of the magnitude of frequency response of the LTI system. Okay, that is how these are related. So we will simulate all these things, and one by one I will consider different signals. In my previous simulations related to autocorrelation function, I have considered 3 signals. Here also same 3 signals I am taking, but in case of one signal I am modifying the duty cycle of the pulse. So I should say that 4 waveforms I am showing to you, and 4 spectral relations of among the spectral relations or time to spectral, all those things I will be discussing. Okay, including the magnitude spectrum also. I will discuss even the magnitude spectrum also, not only power spectrum, not only amplitude spectrum also. Okay, so this is the signal with 40% duty cycle. On period is 40 milliseconds. Off period is 60 milliseconds. So 40 milliseconds means 1 by 40 milliseconds. That is 1 by tau. If this is width is t, 1 by t is nothing but 1000 divided by 40. Okay. So this is nothing but 100 divided by 4. That is nothing but 25. 1 by tau this is basically correct. So this is nothing but 1 by t. What is t? T is nothing but the pulse width here. Okay. So here 25 Hz. That means the fundamental frequency of this is 25 Hz. If you see the spectrum on the right side, this is the spectrum of the input signal, magnitude spectrum of the input signal, capital X of F here. So here, because simulations, we can understand the frequencies easily. That's why, though I discussed it in terms of angular frequency, in the simulations, I am showing it as a linear frequency. Okay, because so that it is easier for us to understand the Hz in place of radians. So here, this is 25 Hz, and this is where 25 Hz first null happens, and this is the sync function basically. Whatever I have here is the sync function, magnitude of the sync function, and actually sync function will be like this. It will go like this. Okay, something like this. So these things which are going negatives will become positives after taking the absolute value. Okay, this is the absolute value. We are not squaring here. It is the absolute value. Okay, so here that is how you got, and this is a sync function. First null occurs at, because it's one-sided spectrum. I am showing one-sided spectrum here, and in autocorrelations I have shown both sides, but here I am showing the one-sided spectrum, only positive frequencies. Otherwise, I will get something like this, and something like this, it is like a sinc function basically. Okay, so I am showing only the positive cycles. Now the first null is at 25 Hz, second null is at 50 Hz. So this is this is 50 and this is 25, this is 75, this is 100, like that. It goes up. Okay, theoretically it is, the spectrum is infinite length. You have so many lobes here, side lobes, and I am showing here up to 500 Hz. Okay, up to 500 Hz I am showing here. And here then, this is what all about the input signal. So then coming to LTI system, LTI system is a low pass filter, and this is the same low pass filter which I used previously, and this is impulse response. And in frequency, when I take the Fourier transform, frequency response, magnitude response of the filter or system, LTI system, is capital H of f. Okay, so this is clearly you can see this as a low pass filter. It is passing all the frequencies. The cutoff frequency, 3 dB cutoff frequency, you can say. Here it is only magnitude spectrum I have shown. And if you see here, if you expand, if you write a vertical line here, this is 0.707 at this point it will cut. That is nothing but 3 dB point. And cutoff frequency, because I have used the cutoff frequency to generate this impulse response at 100 Hz, exactly same thing is reflecting in the magnitude spectrum or magnitude frequency response. Okay, so this is 100 Hz, and of course after that slowly, because the order of the filter, in fact I used all this using some digital filter only, so that I will get impulse response easily, and of course I can use analog filters also, no problem. So here this is because the order is not sufficient, you cannot produce the indefinite, 90 degree slope here. The transition is not sharp, it is gradual, and into the stop band some of the frequencies. These are the frequencies which are passed, highly attenuated but passed. They are passed through the filter or system. Now, so what is happening here? This first lobe is as it is there. So this is the input one, it is passed as it is. And second lobe, that is also passed as it is, because this gain is 1, I have normalized this one. And this is also passed up to this main lobe, and 3 side lobes are passed. And after that, these things above 100, they are highly attenuated. This is what the 4th lobe is highly attenuated, and after almost I should say 130 Hz or 130, 140 Hz, everything is almost 0. Okay, so this is not exactly, it may be from 0 dB at the top, this may be at around minus 80 dB, minus 100 dB, something like that. Okay, so this is now almost not passed, highly attenuated. So these other things here, whatever seen here in the input, they are missing here because they are not passed. Only these 4, including the main, are passed. Other things are not passed. Okay, so what is the effect of this one? Okay, so now let us see, because we have cut down some frequencies. So what will be its effect? So these frequencies are cut. These are the frequencies cut here. So naturally, these higher frequencies are equivalent to sharp edges in the signal. So these higher frequencies, they translate into gradual, because there was a sharp edge here, because you removed so many frequencies. So the signal won't contain these frequencies. Now the edge becomes smooth. Okay, so, and this is anyway as a part of step response, we have something, and of course the impulse response is larger here, so compared to pulse width. So it is not dying here, and if the pulse width would have been larger, this would have become constant here, steady state condition. Okay, but by the time the impulse response has 1, 2, 3, here also 3 cycles, something like that, the pulse is coming down. There is no pulse. So that's why it is stopping it here. Otherwise, in a steady state, you will see a flat pulse here. Okay, if the width of the pulse is taken sufficiently longer. So that's it. Okay, so the cutting down is reflecting into the change of the shape of the input, the output basically. What is this one? This is nothing but output. Okay, so this is the input clean pulse. Output is a oscillating pulse, something like Gibbs phenomena kind of thing. It is not on signal. Gibbs is something different, but oscillations are similar. Gibbs oscillations, and it is not. Not related to return, but not related to system and other thing. It is because it is a signal related to signal. You are cutting down the higher frequency from the signal. That's all. Okay. Now let us consider the autocorrelation function. You have already seen it is a very clean triangular function, and 40 milliHz. This is 40 milliseconds. This is 40 and this is minus 40. Total the width is 80 milliseconds here. 80 milliseconds width here. So I am taking Fourier transform for this. So width has increased double. When I am taking Fourier transform, now tau it is there. I can always, tau it also is a time parameter, and I can also consider this as a signal itself. Okay, whenever I am taking Fourier transform, the input can be considered as a signal. So this is the triangle is a signal now. So this is, for this I am taking the Fourier transform. So now because the width earlier it was 40 milliseconds, now it is 80 milliseconds. The signal or time function, I will say time function has expanded in time. So naturally this frequency will compress. Okay. So that is, again, this is a triangular, not rectangle, and this is not the sync function. Okay, this is not the sync function. It is something else. Okay, square of the sync function, something like that. Okay, it is that kind of thing. Now, but null is occurring at the same place. But here, this slope will change. This slope, how this is falling, this will be different for triangle function and rectangle function. Okay, this slope will change. So here I have Rxy. This is the cross correlation function of input and output. So this is reflecting in these oscillations, some oscillations here as I explained earlier, and this is reflecting into this. And here if you see, so there are, you cannot identify clearly, okay, but there is slight, this contains, because a little bit of higher frequencies here, they are riding on this, so but power is very low, so that naturally must reflect into this one, okay, but you are not able to see that, okay, and this as a plot, again, it looks like a cross power spectral density. So the lower frequencies are correlated. What it means is the lower frequencies in the X and lower frequencies in the Y both are correlated. And up to this, that correlation is there. That correlation is there up to 25 Hz. Okay, afterwards also is there, but they are meager. Now, same thing here, RYY, because this and this, see, RYY, how I was getting RYY as the RYY equal to this RXY multiplied by impulse response. Okay, not input autocorrelation function. Okay, impulse response. That is what is, that impulse response is affecting here. Okay, so this, where is that one? This is the impulse response basically. This is affecting this shape. Okay, this one, this and that impulse response, they are convolved. So I get this RXY and that. That's why I will get this. But here one important thing is, here these symmetric oscillations are there here. Here only one side is there. Okay, other side is not there, because Here this is a skewed waveform. It is falling like this. Okay, it just skews towards right. So it is not a symmetric wavelet. So it is a decaying sinusoidal, something like that. So that's why this when you take RXY, this is one side. When you take RYY, because in this one itself, I have some H of T is there, and again I am convolving this with H of T. So naturally it will become symmetric. Earlier it was asymmetric. This is symmetric. Okay, so that is one difference between all these things. This already I discussed. And coming to this, same things will because here also you are not able to identify much detailed way. So the here and here you will see almost all are same, and these frequencies. Here this third lobe is very low. Third lobe is very low, but a little bit higher it appears for me, this and this. That is because of the addition of these higher frequencies. Okay, these frequencies correspond to, because when you see this cycle, one cycle if you see here itself you can see what is that frequency. From this one you can see, let us say approximately this is the cycle. This is one cycle. And what is this one here? This is 0.5. This is exactly in between. Maybe I will take 1/4. So let us take 1/4 or 1/3. So 1/3 means 50 milliseconds divided by 3. That is how much? 18. So it is 18 milliseconds. So 1/18. 1/18 milliseconds means 3 times that frequency. So that is nothing but 25 multiplied by 3. And 25 multiplied by 3 is 75 Hz. Okay. So that is the reason. Yeah. So that is the reason this part, third one, 75 Hz, this a little bit up compared to this one. This is almost dead. Here, slight improvement is there. Okay. Just because of you can observe those things, okay, because I myself have simulated, and with experience, you can very, very minute changes also. Definitely, if you zoom this portion and see, you will understand very clearly. Okay, so that is what is there. Now I have reduced the pulse width, rectangular waveform pulse width to 20 milliseconds, half of this one. So what happens? 20 milliseconds means 1000 divided by 20 milliseconds. That is nothing but 50 Hz. Okay, so this is 50 Hz. So exactly first null is at 50 Hz now. Earlier it was at 25 Hz. Okay, now it is 50 Hz, and all nulls happen at harmonics of 50 Hz, 100, 150, 200, 250 like that. Okay, and an important thing here is compared to the previous one. So previous one is, see here, these frequencies, they are all very low. The power at higher frequencies above 200 frequency almost nil. Okay, slightly it is there here. Okay, but when you see here, in this case, so these are improved. The power has increased at all levels, ever improved, and 500 Hz is not sufficient to show it is going maybe up to, because this width has null, distance between nulls has increased, that lobes are same, number of lobes are same. So it will extend into up to 1000 Hz, maybe up to 1000 Hz it will get that level where you have seen earlier. Okay, so that is one thing, and impulse response is same again. Then frequency response is same because impulse response has not changed. Now here you will see some difference. Okay, here what is happening here, and because this response, it is this pulse width is less. One thing, pulse width is less. So only 2 cycles of this impulse response is contained in this, and delayed. This delay part is common for both. And here, what was the earlier cutoff frequency? 100. Here also it is 100. Okay, because filter is not changing. Now up to this, first lobe, second lobe. Earlier there were 4 lobes were there. You remember 4 lobes. Now, because I have decreased the pulse width, the spectral width has increased for the input signal. So, but frequency is same. So instead of 4 cycles, I could capture only 2 cycles. 2 cycles are passed through this. The remaining are all zeros here. Nothing is there here. Okay. So that is what is the, and because more frequencies are attenuated. I mean, more frequency means highly attenuated. Earlier these frequencies were also there, but power was very small, and here still they are reduced. Okay, except these two. Okay, third and fourth are also not available here. So this is the equivalent output waveform, and because of this, the waveform is disturbed again. Now let us see the autocorrelation functions. So autocorrelation function, same meaning. I don't need anything here except for this width is decreased. This width has come down. So because this width has come down, this input power spectral density first null, it is occurring at farther apart from the 0. Okay, so here it is occurring at 50 Hz. Earlier it was at 25 Hz. And these are all normal. Same thing you will see in the cross power spectral density and cross, power spectral density of the output signal. In both, the same trend is there, and these are symmetric compared to this. That was low pass filter. Okay, so far we have completed only one simulation, that is only pulse. Okay, pulse of 2 different widths. Now, that too for the low pass filter, with low pass filter. Now, I am going for the high pass filter. And when I take the high pass filter, this is the frequency response. Same cutoff frequency here. Same cutoff frequency. This is not. Same cutoff frequency here, but higher side. It is passing. This is pass band. This is stop band. So accordingly, these frequencies 100. These frequencies are passed. These are attenuated totally because gain is 0. So just multiply this and this 0. Now this is the unity gain, highest gain compared to this. These are attenuated. These are because because this I have normalized basically. That's why I got this. Otherwise, what would have been? This is what I have 0.25 something like that. So this height will be, absolute height will be 0.25. Okay, this will be 0.125 something like that. Okay, because I have normalized after the plot, you are not able to see that again. It is appearing as 1. Basically, this 0.25. This is 0.25. Sorry, this is passed. No, so this is passed, and this is 0.125. This is nothing but 0.125. So that this is equal to 0.125. Okay, so this is the low 0.125, and this is 0.0625, half of this. Okay, so that is what you have. So these are all actually same thing. This is whatever you have, the height will be same, but I have zoomed by normalizing this one. Okay, but you see the important thing is these are cut off actually. Okay, but these are not amplified. They are not amplified. They are passed as it is because your gain is unity here. Okay, so these are not amplified. These only zoomed in my simulations. That's all. And this won't contain any low frequencies. No low frequencies at this. When you transfer this into inverse Fourier, not inverse. I can take that not for magnitude. I should take include the y of f, not modulus of y of f. I should include the phase also there. Then you take inverse Fourier transform, you will get this kind of signal. Okay. So here again, these edges are, you can identify the edges with sharp changes here, and the impulse response oscillations are appearing here and here. Now same thing, autocorrelation function. Input is same, filter is different now. Okay, filter is high pass filter. So this is the, directly I will come to this, is the output of high pass filter, which we have seen earlier. The spectrum of this is nothing but this, the power density spectrum. Power spectral density is this. So this also contains same thing. This is this is not one. Okay, this you should reduce the power as whatever is there here. So this is 100. This is what maybe this is equal to 0.01 something like that. Okay, so this must be half of that one, 0.005 something like this. Okay, now periodic signal I am taking. Periodic autocorrelation function is also periodic, but you have an envelope like this. Okay, that is because this is tapering. It is tapering like this because you have taken a gating pulse. You have taken only 4 cycles. If I take infinite cycles, all these things will go. Okay, so that is what you have, and you have to multiply these two to get this. These two must be convolved. So when I am convolving like this, as I told you, these are the, because of these components I am getting. Okay, now this wave shape is known. It is only extension of the previous one cycle. Another cycle, if you expand, you will get like. And this is, I will come to the simulation. Different pulse width here, and periodic narrow pulse width. So you have, important thing here is basically what is happening is, because of periodicity here there is a line spectrum. There is one line here developing. So the spectrum main lobe is splitting in as a line spectrum. Because of line spectrum, it is splitting because of this. And the split is not perfect because the cycles are not infinite. Okay, the split is not perfect. Because the number of cycles are only 4, and the effect of 4 is there is a DC component in this. Okay, so 4 cycles, this is the positive value, and area under this plus this plus this plus this 4 areas add, divided by 0.4. This is 0.4 seconds divided by 0.4 seconds. So that is the average value of that. There is some average value here. Okay, and if I take this pulse to the center, let us say -1 to +1, if I take, or -0.5 to +0.5, if it is a bipolar signal, then this DC won't appear. Okay, so there is a spike at DC also. So that is what you have here, and this spike you are not able to see in a single case because the energy spectral density, and it is a continuous spectrum, and this is a discrete spectrum or line spectrum we call, and you are able to clearly see this line. Okay, so same thing, this is passing above 100 Hz are passed, other things are not passed. Then this is reflecting, this is the first. So this first bunch is totally discarded here because of this 0 gain, and this second one, I will change the color here. So the color has changed now. So this is the second lobe. Second lobe is also split here because there are splits here. There is one line here, another line here. This is a line spectrum. So similarly, this is magnified. This is magnified, and this is the lobe corresponding to this one. Sorry, not here. This is the above 100 is this one. Okay, so not this. You have above 100 means here there is line spectrum here everywhere, and this is magnified to this. Of course, this is not very high. This is less than, here whatever is there, it is less than 0.2 something like that. Okay, so next. So here, if I take this one, this corresponds to this. Okay, so here same trend is appearing, slowly coming down, but all powers are magnified here. Okay, so that is what you have the thing here, and so this is the autocorrelation function, same autocorrelation function as earlier, and this is again, it was a spectrum of a triangular waveform, so it is a square, it is like a sinc square, it will become a sinc square, I mean not exact sinc square but shape wise, and but it also has spectrum here. It is a split, there is a split here, and there is a DC value here, there is a split here. Okay, now but these components, they are not passed in the output, so above 100 only pass. This is what is the first one passed, and this is corresponding to that one. This is less than 0.1 or 0.05, something like that, very less. Okay, so this is not the actual value, absolute value. So similarly, these small things, these are all small things here, but they are all magnified here because of the high pass filter action. Okay, so this is what you have, and when you see here, because there we could not see properly, but when you see high pass filter output, so basically what is happening here, this is one output, this is another output. The autocorrelation function is also periodic, and it contains bunches. Okay, it contains bunches, and of course R naught, this at tau equal to 0, this is as usual it will be high. So others are there. So it is a and it is not periodic, because if I take the infinite cycles, here also I will get, this also will increase. They will become flat. Autocorrelation function of the output also will be periodic. If I consider instead of 5 cycles or 4 cycles, if I consider one number of cycles, I will get that one. Okay. And because I have taken 4 cycles, here this is 1 cycle, half of this, all positive side. Second cycle, third cycle, fourth cycle. So these 4 cycles are reflecting as a periodicity in the autocorrelation function also. Okay. So this side also negative side, 1. This side negative, from here 1, 2, 3, 4. Okay. So that is the same thing with the output also. So I mean, this is all, I think maybe in the next class I will go for another new signal, that is linear frequency modulation. I will show some other signals also, and some more results I will present. Okay. So thank you for your time.
Like, share and subscribe. Hit the bell icon for more updates.